Welcome everyone. So this is our 66th live stream geometry. Today I'm doing problems from the Balkan Math Olympiad Shortlist from a couple different years. So that's the same contest I did last time. We have two people here with us. I know another person's going to join in a couple minutes, and probably others will join too. So if you'd like to join our session in the future, feel free to email me at mgreenb801@gmail.com. The sessions are at 8 a.m. US Central Time. So I am going to share my screen. Hey, Melek, thanks for joining. Let's see. So let me share. Hold on, just here we go. All right, so this problem was from 2017. Oh, in case you guys notice, my background is different because I'm at my parents' house now instead of my own apartment. So, all right, so we have an acute triangle ABC with circumcenter O. And then we draw the three midpoints. Oh, actually, you know what? So Khan, he's joining us in 15 minutes, but he said he wanted to go through this problem. So I'm gonna wait till he hops on before we get too much into that. So here's a problem involving isogonal conjugates, or it looks like it. I haven't gotten too deep into it yet, but we have a triangle ABC, and P and Q, I think the condition means they're isogonal conjugates. The only thing, yeah, I got to learn more about isogonal conjugates. I just haven't had much time lately, but the only thing I really know is that they have the same pedal circle. All right, we have someone else joining us. So let's see. Hey, BJ, thanks for joining us. So yeah, I'm going to draw the pedal circle. I feel like this might be the fastest way I know to draw isogonal conjugates. So PAC equals QAB. Okay, actually it says let D and E be the perpendiculars to BC and AC. Okay, so maybe it would be better if I made this A, or no, I made this C, and this A and that B. Oh, actually, it has the perpendiculars to all three sides. So, okay, so D, from P to BC, so this is D, E. I'm going to have to rename this later, but I'm going to draw the pedal circle. So that's the circle through the 3 foot of the perpendiculars. And then the isogonal conjugate. Let's see. So F is the foot of the perpendicular from Q to AB. So this would actually be F. So we'll call this G. And if I drop perpendiculars here, then that point should be Q. So this is using the fact about isogonal conjugates, that they have the same pedal circle. And then M is the intersection of DE and AB. Okay. And we want to prove that MP is perpendicular to CF. Let me just move things around here. So this is M. And okay, I'll just call this point something. So we know that Q I don't like I, I'll call it J. So QJ is perpendicular to AC. Let me hide some of the stuff I don't need. Okay, but I'm going to draw all the perpendiculars. So this, there we go. Maybe I'll hide this for now. Oops. Let me draw this, hide this. All right. So I think that should do it. And we want to show MP is perpendicular to CF. So really all this means is that, oh, are these collinear? So it looks like Khan just joined us. Hey, Khan, thanks for joining. So yeah, I just skipped over your problem, but we're going to come back to it after this one. So basically this just means, yeah, if you have two isogonal conjugates, I don't want to make it look like C, P, and G are collinear. Okay, so yeah, these aren't necessarily concurrent. So yeah, this just says if you have two isogonal conjugates and you take these 2 feet of the perpendicular and they intersect AB at M, then MP is perpendicular to CF. That's interesting. This almost feels like it should be like a well-known property or something. It almost feels like poles. Yeah, I was going to say it feels like poles and polars, but like this isn't tangent to the circle. So maybe not. Sometimes I like to drop a perpendicular from P to CF and then try to use the radical axis theorem. What if I try that? I wonder if the midpoint of PQ lies on CF. I don't think it does, but let me just make sure. Yeah, that doesn't lie on CF.
Can you intersect CQ and MD?
CQ and ED?
Yeah.
Okay. All right.
Can you check that if MPI and CQF are similar?
CQF and EG. Okay, so all right, looks like a Khan is joining us. So CQF, that's 154, and MPI, that is it looks like that angle's the same. Oh no, it's not. Okay. All right. Check the chat. Is CQ perpendicular to DE? Let's see. Is it? It looks like it might be. Let me check. Here it doesn't look like it as much. Oh, I think it is. Is that obvious? Let's see in the chat. Yes. So do you guys know the proof of that?
The CP goes through the circumcenter of the CED.
Okay.
And the orthocenter and circumcenter are isogonal.
That makes sense. Okay. Interesting. So this is these are perpendicular. And we want to show this is perpendicular to that. So that would make so if MP was perpendicular, we'd have like a cyclic quadrilateral, right? If we like took the intersection of MP with CF. Yeah, maybe I could do it that. Oh wait, do those really concur? No. But basically, if we let K be the intersection, then we're saying MKIC is cyclic, right? So maybe we could prove it that way. ED PK. Oh yeah, and PG FK would also be cyclic. So yeah, really, if we can prove that any of those are cyclic, that would solve the problem. Yeah.
Can you define K other opposite side? It is the intersection of the circle CE, PD, and the line CF. Then we are done by radical axis.
Oh, really? Okay. Okay, so I'm going to hide MK for now, or I'm just going to redefine K basically as the intersection of this circle.
Yeah.
And then this circle, we would also have this circle because this would be 90 degrees. And then by the radical axis theorem, oh yeah, that's a quick one. Okay. All right. So we didn't even need that these are perpendicular really. So P and Q are isogonal conjugates, which means they have the same pedal circle. All right. And so I'll say label the phi of the perpendiculars as shown. And let K be the perpendicular from P to CF. Whoops. Oh, but I want it to look that way. Yeah. Okay. And we get two cyclic quadrilaterals, and then we can use the radical axis theorem, and that solves it. So you have angle PGF equals PKF equals 90, and that means that PGFK is cyclic. And then we also have angle PKA equals angle PDA, which is equal to angle, these should be C, equals angle PC equals 90. And that means that PK DCE is cyclic. PKC is PDC is PEC. And then by the radical axis theorem, DE, GF, and PK concur. I'll say concur at M. And so then it follows that MK is perpendicular to CF. All right. So I'll move on to the next one. So yeah, I didn't really use anything super special other than isogonal conjugates have the same pedal circle. Actually, we don't even need Q. Oh yeah. Well, yeah, we could just use the pedal circle, I guess, and then we don't need Q. So here is the next problem. So Con, this is the one that you sent me. So we have an acute triangle with circumcenter O. All right. Then the midpoints of the sides are D, E, and F. So B, C, C, A, and AB. And an arbitrary point M on side BC is chosen. So I'll let this be M. AM and EF intersect at N. And then we draw ON. It's kind of interesting. ON cuts the circumcircle of ODM at P. So obviously OD is perpendicular to BC. And so that's point P. And it says prove the reflection of M over the midpoint of BP lies on the 9-point circle. So basically the point that makes a parallelogram. So MPD and that point would be a parallelogram. Okay. So yeah, I don't even know if it's worth drawing that point for now. We just know that this is a parallelogram. We're saying that's on the 9-point circle of ABC. Okay. That's kind of interesting. So as I move M around, this should like trace out the 9-point circle.
Can you draw OD?
Yeah. So AN equals NM, we know that. Yeah, let's see. How do we want to do this?
Actually, the diagram is okay, I think.
Okay. I don't want to make it look like EM prime is perpendicular, but I think we can, yeah. But yeah, I was just curious, as M gets closer to point D, M prime doesn't approach D, it approaches some other point. So if M approaches B, then I think M prime approaches E, right? Yeah. This is a cool one. So yeah, we could use angle chase, we could use power of a point. I think wondering what the best way is. Maybe it's worth drawing the 9-point circle, and well, I wonder if there's some other point on it that's special. Okay, I'm gonna erase it. I like this problem. So we know OM is a diameter, or is that true? How did we define this? I forgot. Well, yeah, because this, yeah, OM is the diameter of this circle. Maybe it's worth drawing the center of it. Because then, just a guess, but then NH is parallel to OA. I don't know if that helps.
Can you draw the ortho center of ABC?
Yeah. Yeah, I'll call that at 1H instead. Oh, does it not like that I already called something H?
Yeah,
Maybe.
you should change it.
Oh, it's switched that to being the H actually. It deleted the other H. That's interesting. Okay, so this is the orthocenter right here. Sorry, it's just sticky. I want this. Call this J. So yeah, let's think of the best way. Angle chase, power of a point, or we could even use homothety, like if we draw the 9-point center. I'm going to do that. Like maybe if I draw the 9-point center.
You're not drawing.
Yeah, you're right. Oh, whoops. Maybe, yeah, maybe I can use homothety to show it. So if N is the 9-point center, maybe I could show that NM prime is half the radius. Oh, I don't want to call it N. I'll call it Q. Yeah, I'm not sure how helpful that is. It's the midpoint of OH, though. Maybe I could do something with that. Yeah. So we'll draw the circle of AEF. Yeah, it passes through O.
Can you intersect this circle with OP?
With OP?
Yeah.
Yeah. Sorry. Yeah, GeoGebra often just double clicks. So we have a point. I just don't like I always have to change it. So I'll change it to K.
Okay, I think we can finish now.
Okay.
We know AK is perpendicular to OP. So by Thales, N is the midpoint of PK.
N is the midpoint of PK.
Yes.
Okay.
And yeah. And which means AK equals dm prime.
Okay.
So AM prime is parallel to DK.
Okay.
So DFEM prime is similar to AEFK. So if DFEM prime is concyclic, then AEFK is concyclic too. So we are done.
They're actually congruent, AEFK and D. I
Yeah,
see.
congruent. Yeah.
Ah, that's nice. I like that. That's cool. So I'm going to start typing it up. I'm going to delete a couple things that I don't need for that. Okay. Check the chat. So let OP intersect the circle AEF again at K. So first of all, we have AN equals NM. And since EF is a midline, and then we have AO is a diameter of the circle. So angle AKO equals angle AFO equals 90. And since angle NPM is also 90, that means A and K is congruent to MNP. So that means AKN is congruent to MPN. Add the triangle here. So AKMP is a parallelogram. So KM, let's see. So yeah, we have, well, yeah, actually we just need AF is equal to MP is equal to DM prime. Yes. So oh yeah, so that makes that a parallelogram. So hold on one second. So AK equals MP equals DM prime. DM prime. And so basically that means that, yeah, and also AK is parallel. Yeah, KD is parallel to AM prime. Because, yeah, AK is parallel to MP is parallel to DM prime. So basically combining the above, AKFE is congruent to DM prime EF. AKFE and DM prime EF. I think I'm prime, right? And then once we know that, since AKFE is cyclic, then DM prime EF is cyclic. So and that means that the reflection of M over the midpoint of VP lies on ABC. Lies on the 9-point circle of ABC. All right. So that was a fast one. And I'm just going to add up here. It's pretty obvious that MPDM prime is a parallelogram. I just didn't state that. All right, so we'll move on to the next one. Oh, when you say original solution, is that the one that they gave for the contest, or was that the one you found? Okay, so this is the next one. So we have the 3 altitudes of ABC. Oh, you searched the original solution. I will draw the 3 perpendiculars. Okay. So AD, BE, and CF. Then we reflect E and F over AD. And they make it easy because they just call it E prime and F prime. This is H. BF prime and CE prime intersect at X. Okay, so I'm going to have to draw the whole ray. These intersect at X. And BE prime and CF prime intersect at Y. This almost looks like Pappus's theorem or something. Maybe Pascal's theorem. Okay. Those intersect at Y. And we want to show AX, HY, and AX and HY concur on BC. This almost looks like it's like Pascal's theorem or something. So, all right, I'm going to hide a bunch of stuff. We don't need to see the whole line here. And I'm going to want to draw CY and BX. Okay. I wonder if DF prime.
Draw the circle with diameter AH.
Okay.
Everything lies on it.
Yeah. Okay.
And now this looks like some Pascal theorem.
Yeah. So why does Oh, by symmetry, F prime and E prime are both going to lie on it. And then we have to show X and Y lie on it. So is that true by Pascal that X and Y lie on it? Well, how do we know X and Y lie on the circle? Is that obvious by Pascal?
Actually,
I'm
I
not
don't
sure.
think we use Pascal to prove that they lie on the circle, but instead we use Pascal to prove that the three lines are concurrent.
The three lines concur on BC. Yeah.
Yeah, we use Pascal for that, but to prove that the 2 points lie on the circle, I think we're gonna use angle chase or something.
Angle
I don't
chase.
think it's hard.
Okay. So,
Actually, it's trivial, I think, because the reflection of E over AH must also lie on AH. The
yeah.
and
So E prime and F prime, I know why they lie in the circle, but how do we know X and Y lie on the circle?
That is equivalent to showing that Y lies on ABC.
Okay.
And also similarly that X lies on HBC.
Okay. So yeah, if we could show either of those two, that would solve it. So I wonder, so it might be just an angle chase because the angle like HBX, it's half the difference between arc XE. Oh, but we don't know X and Y in the circle, so we can't use like arcs. But we know F prime lies on this. Well, yeah. Is it obvious that D, F, and E prime are linear? That would probably just be an angle chase, right? Let CE prime cut the circle at X. Okay, so let's hide this and this. And we can call this X prime. And we can call this Y prime. And first of all, is it obvious that do we even need that E, F prime, and D are collinear? Or is that, oh, I guess that's obvious by Blanchett's theorem, right? So, yeah. All right. Okay, so show by Pascal that X, F prime, and B are collinear on that. Okay. All right, so I'm going to start writing this up. So basically by Blanchett's theorem, that's how we know D, F prime, and E are collinear. So FDA equals angle EDA. And that implies D, E, and F prime are collinear. Hold on just a sec, I'll explain it. And so are D, E prime, and F. So Blanchett's, you can also prove it by an easy angle chase, but Blanchett's theorem says that even if H isn't the orthocenter, if you pick any point on the altitude, and then you draw the line CH and BH and you let it intersect the sides at E and F, then angle FDA is going to equal angle EDA. So even if instead of the orthocenter, even if I chose a point down here, and I drew E and F, then those angles would be the same. Okay, so now I'm going to use Pascal's on the hexagon that Hakan said. So let CE prime cut the circle AEH at X, or X prime. I'll say, and let or CE prime, yeah. Sorry, that's what Hakan said. And then let BE prime. Wait, why is it not BF? Oh, CF prime. Oh, let BF. I'll just say, and let BE prime cut the circle at Y prime. So first I'll just start out by saying angle AEH is angle AFH is angle AE prime H is angle AF prime H. So that means that AE F prime HFE is cyclic. Okay, so by Pascal's on that, X, F prime, and B are collinear. Let me actually think about that for a sec. Okay, so we have E prime. Oh, I just renamed things X prime, but so this means that X prime equals X. E prime X prime F EAF. Okay. Because EE intersects F prime at the point at infinity, and then EX prime and AE intersects at C, and then AH and EF prime intersect at D. So the other two have to intersect at point B. Okay. So that means that X prime equals X. And then similarly, Y prime equals Y. We don't need that. We don't need to denote x prime. By reverse Pascal. E. Oh, I've never heard of reverse Pascal. It's like the converse of Pascal you can use. Interesting. So, okay. I'll say, or we can use reverse Pascal. Yeah. Lie on a conic. Okay. And then similarly, y prime equals y. So let me draw this too. All right. Similarly, y prime equals y. And then we can use Pascal one more time, and that finishes it off. So we want to show AX and YH meet on BC. So it would be AY. I guess just AY F H F prime X. I probably should do it, right? Yeah, AYF HF prime X. Then we have YH and BC can, or YH and AX concur on BC. All right, so this was an easy one, or easier one. Okay, so yeah, we didn't actually need to denote x prime. Yeah, so I could yeah, really this could just say x. Okay. All right. Very nice. Whoops. So this is our third problem, and it's not even 10 yet. So yeah, maybe these are a little bit easier. Let's see. This one, let's see if we can find a harder one. Yeah, these are all, it's up to you guys. I'll just stick with these for now. But yeah, next time I think I'm going to take some problems from the book by I3435, so they might be a little bit harder. But yeah, this session may be a little bit easier. Okay. So we have an isosceles triangle with AB equals AC, and M is the midpoint of BC. Then we take the perpendicular from M to AB. Obviously, AM is perpendicular to BC. Okay. Then this is point H. And D is an arbitrary point. I feel like if it's arbitrary, makes the problem easier. E is the intersection point of the line through B parallel to HD. With the parallel line through C to AB. Oh, that's kind of interesting. So parallel through B to HD with the parallel through C to AB. Okay. So I'll draw something like that. So this is E. And then we want to show DM bisects angle ADE. That's interesting. Okay. This is a weird configuration. That's CE. I drew DM. Now I need to draw BE. And I think that's all I need, right? Oh, I need the perpendicular. It's kind of interesting. So you want to show angle ADM is angle EDM. Is AEM isosceles? I don't, no, it's not.
Looks like ADM and MDE are similar.
Oh, really?
Yes, but it is MD isn't the angle bisector of AME.
Okay, so they're similar, but like not, it's not an, yeah, I see what you're saying. It's equal to angle DEM instead. Whoops. So that's angle DEM, and that should be equal to angle AMD. Yeah. Okay. Let's see how we can try to prove that. So we want to show AD over DM is DM over DE. These triangles almost look isosceles, so let me make it look, yeah, we want to show AD over DM is DM over DE, or AD times DE is DM squared. It almost looks, is D the orthocenter of A? No. One sec, guys, I'll be right back. All right, thanks for waiting. Actually, once. But yeah, it's interesting that those are similar. I wonder if we can reflect B over AM, and then we would have like a spiral similarity. Oh, but it wouldn't be. No, we want to draw the point that makes ADM a parallelogram, I feel like. So, sorry, I see someone wrote something in the chat. Just a sec. Oh, but that wouldn't lie on AB. Maybe it's still worth drawing that point. So, yeah, ADM. Yeah.
D should be the HM point of AME.
Oh, really?
Yes. Well, that would be true if the angle conditions were true.
Okay. The HM point from A, I'm guessing.
From M.
Oh, from M.
Actually, maybe the dumpty point or something like that. No, it isn't the HM point exactly, but
Okay.
it is like that is the perpendicular from circumcenter to the C median line, I think.
Oh, really? The Dumpty point?
Yes, I think it is defined like that. And in this case, it should be the dumpty point.
Okay. The perpendicular to the symmedian. Yeah.
Better not draw C medians. I think they won't help.
Okay. So did you say it doesn't look like D would be the perpendicular from G to the symmedian?
It is the dumpty point from M. So MD
Okay.
is this median.
Oh, okay. Interesting. Yeah, I guess I'm gonna delete D prime for now. So yeah, that's okay. So yeah, first of all, yeah, can we show angle GDM is 90 degrees? Or maybe we could use ratios to show that AD times DE is DM squared. I guess there's a couple things we could try. So I wonder, let's see. Yeah, we need to know the angle before we know that. M has to be the eccentric of E and BEC. Interesting. Let me think about that. So yeah, why is that? So angle bisector BC. MC is a bisector. Yeah, because MC is the bisector. Yeah, because this is an isosceles triangle. So since EC is parallel, yeah, it's an external bisector. CM. Oh, that's right. Um, yeah, so we need to show that M is the X center of EDC. That would solve the problem. It's all right. Do we use like the in center X center lemma or something? Because yeah, I think the angle bisector here is perpendicular to BC, right? Yeah, so here maybe we can use the in center X center lemma somehow. Let me see who's on. Oh, looks like Serdar had to hop off. Okay, but yeah, we know it lies on this bisector. How do we show it lies on a different bisector?
Which bisector does we know? Do we know?
We know that CM bisects. So basically, if I draw, whoops. Let's say I draw these two rays from point E. We know that CM bisects this angle.
Oh, okay.
Yeah. If we can show that EM bisects this angle, that would solve it. Or if we can show somehow that M is the X center of ECD. Maybe there's something special about the X. Oh, but HM is perpendicular, so maybe it's a good idea to draw this. So MH is equal to MJ. So we want to show, if we could show MJ is like the radius, or yeah, if we can show MH is the radius of the X circle of ECD, that would solve it. Yeah, there's a couple of equivalent ways of seeing it. Let's see, distance from M to AC.
Yeah, we already have that because M is the midpoint of BC. So if we drop a perpendicular from M to AC, then it's
Oh,
like
okay. So it has to be. So we know that M lies on one of the bisectors, and we also know it has. Well, yeah. So we know M has the same distance from AC and EC. Yeah, we want to show it has that same distance to ED. Yeah, exactly. Oh, sorry. Yeah, I don't know if the circle tangent to CD and CE. Well, no, there's infinitely many circles where the yeah. We need one more fact. Sorry. Yeah, we need the distance from M to CB. And I wonder if it would help to draw the in-center of CDE. So let's see. Like do these three concur? Let's see. Yeah, looks like do these concur? It's hard to tell. I don't think they do. No, I don't think those all concur. Yeah. Does G lie on the bisector of DC? It almost looks like that. Huh. Is that obvious? Yeah, it looks like G. I'm sorry.
That is true if we would solve the problem
Oh, okay.
because of the dumpty point and the external and the internal bisector stuff.
Okay. Yeah, we haven't used much about point H. Maybe it's worth drawing this point so that we could use ratios. Yeah, we have to use H eventually. I'm going to delete this point J. I don't think it does too much. Um, This is harder than it looks. Okay, so is MG perpendicular to EI? No. I wonder if MID is similar to something. So ADI is similar to DEC. Feel like maybe that would help. So yeah, we want to find something about the distance from M to DI. M would also be interesting. Yeah, it would be the x center of ADI also. So it'd be like a double x center. So yeah, let me draw the X circle because it seems like there's something special about the X circle. I don't know how I missed. Well, yeah. So basically, we want to show the circle with center M through H is the X circle both, right? So that's kind of interesting, because that means if we move D around, basically H is staying the same, but if we move point D around, it's equivalent to MI is perpendicular to ME. Interesting. So if MI is perpendicular to ME, does that mean AIM is similar to EDM? No. We want MI and MD to be isogonal. Yeah. Wow, there's so much stuff going on here. So it's almost like, what if we just started out by drawing the circle with center M and radius MH? And then we pick a point on it and we draw the tangent line here. And then we want to show, yeah, so what if we rephrase the problem? So we start with the circle centered at M and radius MH. We pick a point J on it. We draw the tangent line and it cuts these three at I prime, D prime, and E prime. Yeah. Yeah. So actually we could keep D as an arbitrary point, and we could draw the tangent from D to the circle, and we could call this like E prime. And then we want to show E prime, yeah, HD is parallel to BE prime. So then we'd want to show BH over HI is ID over DE prime, but ID over DE prime, that's also AD over DC, and that's also AI over CE prime. So yeah, that might be an easier way to think about this. Call this K. So BH over HI, HI is the same as IJ. I don't know if that helps. BH over HI is BH over IJ. And then IJM is a right triangle. And BHM is also a right triangle. So maybe we could use similar triangles somehow. Because BH over HM, yeah, I feel like that might be a way to move forward with it. Because yeah, if this is actually a right angle here, I wonder if BD is parallel to HJ. That would mean BD is perpendicular to IM. Let's check that. It's not true. So IH over ID is IJ over ID. It looks like we're so close, but I just can't finish it. Is triangle IJB similar to something? Actually, is IM an angle bisector here? Oh yeah, IM has to be an angle bisector because M is a center. So
if we let like AD to be constant, then could we compute like we should be able, but can we compute AI and ID?
If AD is constant.
Yes, like in terms of AD.
Maybe.
And of course, in terms of the triangle and the line segment AD.
So we know that AI over ID is DE prime over E prime C. I don't know if that helps.
Can you repeat?
Oh, I just said we know, basically we know triangle AID is similar to DE prime C, so maybe that helps.
Yeah. I wanted to compute HI because HI is the only problematic here.
Yeah. All right.
But if we know AI and ID, then we can compute HI.
Okay.
And if we know every side of AID, that's triangle.
Okay. Well, we know, so AD over AC is ID over IE prime. I don't know if that helps. Maybe we could just show angle IHD as IBE prime. Let me try something. So angle IBE prime is equal to angle BE prime C. So yeah, E prime M is a median in this triangle. Maybe that helps. I wonder if JHD is similar to EBC, E prime BC. No. Oh yeah. I feel like there has to be a synthetic solution, but yeah, you can still post it. Okay, maybe MKE prime is similar. Is MKE prime is a right triangle? Is AJ perpendicular to HD? No. Okay. So I define E prime as you draw the tangent from D to the circle and it meets this parallel through C to AB at E prime. Let me draw MK. So basically, yeah, we want to show angle triangle MIH is similar to E prime MK. Oh, you know what? Okay, so I think in this configuration, we can show, I can show that angle IME prime is a right angle. I think I'm pretty close here. So I know IME prime is a right angle. Yeah, IHM is similar to E prime JM, exactly. So IH over HM is E prime is intersection of TMB and I'm a little confused by what BJ said, but yeah, so we want to find IH over HB, but we have a bunch of similar triangles. And yeah, HM and K are collinear. Yeah. So yeah, we want the ratio ID over DE prime, which is AD over DC. Okay, I think I might have a solution here. Let me just think through it a little bit. So BH over HI, that's the same as BH over HM over IH over HM. Then BH over HM is CM over AM. Yeah, we want HI over HM is JE prime over JM. Wait a sec. So yeah, hi times ek, e prime k is the radius squared. So hi times ek is hm squared. Yeah, it looks like we have too many ratios here that has to solve soon. Because like, okay, so we would have, what segments are involved? E prime k, cm, yeah, I'm a little confused now. Okay, you guys want to move on to the next problem? Or do you want to try this for a little longer?
Let's stay for like 10 minutes or 15 minutes.
Okay, I'll try it for another 10 minutes. So yeah, ID over DE is AD over DC. Can I label where CK meets AM? Yes. Oops. Sorry, let me just shrink it a little bit. Okay. There's a cons proof. Okay. All right, let me hide this. I'm going to change it from E to, I don't know, L. Okay, BH over HI and E prime D over DI. And so once you show they're equal, That would solve it. So BH over HI is MB over MI. Times that. Yes, I'll draw BL. So we have a rhombus, basically. Yeah, I'm just reading through Hakan's solution. But yeah, if you find a synthetic, let me know. Yeah, oh, actually, actually, maybe that's not obvious. No, I think I got confused. I don't think it does. Okay, let me read it one more time. So we have MB over MI, sine HMB over HMI, but MB over MI is sine AIM over cos HMB. Oh, DDIT? Yeah. So yeah, I'm reading Hakan's proof. I'm not sure so how he gets MB over MI. Let's see. Well, if signs an MIB. Oh, okay. That makes sense. Also, E prime D over DI is equal to it almost feels like there has to be a way to simplify that trig, because like angle HMB is just angle BAM. Like, yeah, I think. Sorry. Oops. Sorry, it keeps slipping my mouse. E prime D over DI. It's cos DME prime. ME prime over MI. Sine AIM over cosine AIM. Okay, I see what Hakan did. Let me think if I can simplify that. MB Yeah, it looks like there has to be some similar triangles. That's what I'm thinking. Like, I'm trying to think how I would do the similar triangles. So yeah, E. Yeah, because nothing in that proof looks like it should be able to be done without similar triangles. So yeah, the first part of it, we can do it just with similar triangles. And the second part of it, ED prime over DI ME prime over MI times sine DME prime over cos. So, okay, redefine E such that CE is parallel to AB. And if ED meets AB at I, then MID equals MIB. Doing it, M is the X center of DEC. Yeah, we've been trying to do it that way for a while. So yeah, so that's why we called it E prime. But that's exactly what we were trying to do. I'll just write out, yeah. Oh, it's all right. I'm going to write out Hakan's proof for now, and then move on. And if we solve the rest, we can come back later and try to see if we can find a synthetic solution. Oh, does MI equal ME prime? No, this is a right triangle. So that would mean it would have to be, yeah. Okay. So yeah, I just have to put okay, so basically, here's the, yeah, I can move this picture to the right a little bit since it's a tall picture. Okay. So then we would have BH over HI. So yeah, I'll write what we did up here. So draw the circle with center M and radius MH. I'll give it a name. Does E prime M pass through the tangency point of BL and the circle? Let's see. Yeah, no, it doesn't look like it. So let E prime be the intersection. Then draw the tangent from B to omega. Let it intersect the parallel through C to AB. At E prime. And then we have the calculation that Hakan just gave. And so this means that BH over HI equals ED prime over DI. And that means that HD is parallel to BE prime. I'm sure there was an easier solution. Yeah. So yeah, we'll go back to it if we solve the rest. And so then E prime equals E. And so DM E, and that means that M is the X center of EDC. The E X center of CDE, and that implies DM bisects angle AD. All right. So yeah, we will come back to this if we have more time and see if we can find a synthetic solution. So I have 2 more problems left.